Hey, hi, this is Mr. Secoder. In this video, I'm going to discuss or explain a solution to our educational code force round 87 problem E, graph coloring problem. This is very exciting problem. Here we use the concepts of bipartite graph, we use the concept of for depth first search, we use the concept of for dynamic programming. So we use these components. So this problem is very exciting. Today I would like to discuss the solution to this problem. Let's go to the question first and let's read the graph coloring problem. So you are given an undirected graph without self loops or multiple edges, which consists of n vertices and m edges. You're also given three colors, you call three color counts. Okay, we call that as n1, n2 and n3. So he asked it whether we can label each vertices with one of these three numbers 1, 2, 3 in such a way that each vertex should be labeled by exactly one of this number, not 2, it's one of this number. We have to label the nodes vertex. The total number of vertex with label 1 should be n1, similarly label 2 should be n2, label 3 should be n3. So it would be exactly matched. And there is one condition that if you color two nodes that are connected to each other with the color U and color V, the absolute difference between these two color values should be 1. That is, if you colored one node as 1, the adjacent neighbor node which is connected through edge should be 2. It should not be 3. Similarly, if you connected you can connect 1 and 2, you can connect 2 and 3, but not 1 and 3. Okay, so if there are multiple valid labels, you can print any of them, and you can see that the constraints is n is between number of nodes is between 1 and 5000, and m can be 0 and n power 5. Okay, so he is given that the condition that n1 plus n2 plus n3 is equal to n. So we can reinterpret this fifth condition in a different manner. So here we can connect 1 and 2, we can connect 1 and 2 and 3 and 2, but we cannot connect 1 and 3. So here we think of parity. Okay, so 1 and 3 is a odd parity. Okay, 2 is a even parity. So this we can interpret this as a bipartite graph. So what we do is we first check whether this graph can be broken into bipartite, because in one of the partition of the base bipartite graph, it contains color 1 and color 3. In the second partition, it contains the color 2. Okay, so we need to partition in such a way. Okay, so we can use the DFS in order to check whether this can be a bipartite graph or not. And what we do is while checking this, we'll keep track of what are the nodes that are involved in a bipartite. Okay, and one more thing is this, if this is a single connected component, this problem would be simple, very easy. We can run this DFS and find whether whether one of the partition is matching with the n2 color and other partition is matching with n1 plus n2 color. But this is not only a single connected component. We have multiple connected components, that is disconnected component. Okay, so in this case what we do is each component can be painted independently. Like that is, we can use this n2, that is second color label number 2 color, independently to each of this partition. I will show you the sketch pad. So for example, this is a graph that you are given. So if you color 1 here, you can color 2, and this node should be 3. It should not be or 3 or 1. It can also be 1. Now this node can only be 2. It cannot be 1. So what we are doing is we are partitioning. So 1, so color with 1 this side, and color with 2 this side, and the color the third color should in some other partition, and the color 2 is this partition. We are actually partitioning into, this is actually node. Okay, these 2 colored nodes and this 3 color node. So we have edge like this, and from here, from these two nodes we have this edge like this, and from these two nodes we have this edge like this. Okay, so we are actually partitioning this. So if this condition should met, there should be a biparate graph. This is one partition, and this is partition. Let's call this as a 0th partition, and this called as a 1th partition. Okay, or you can call it as a first partition and second partition also. So if this is a single connected component, this you can run a DFS and check whether the graph is biparate or not easily. But this is not there can be a multiple components. It is disconnected graph. What this disconnected graph was given. So what we need to do is so let's say in the first connected component, in isolated component, it's a one connected, let's call it as component 1. In this component, if you have 0 connected components, okay, we call in this way, we build a table like this. So this is a partition, which partition you have. Okay, this is component, which component. So what we do is, so you count how many 0 partitioned in this component exist. We biparate all these sub components. Like this is one component, right? We may exist similar kind of component other. So what we do is see the similar way we partition this graph, we also partition the other graph, and we keep track of how many how many nodes exist in 0th partition and how many nodes exist in first 1th partition of every component. So for the second component, we'll keep note of here the first component, 0th component is 2, right? And first partition component is number of nodes is 4. So similarly here we'll note how many it can be formed if other component exists. We'll store in this way. Not only the count, we also store the nodes. These actual nodes is there, right? So we'll keep so this can either belonging to a 0th partition or 1th partition, right? We'll create some array called partition. There we'll store this specific node ID having either 0th partition or first partition. If this is belonging to the here, the one belongs to a 0th partition, right? So we keep that as a 0 here. If this belongs to one partition, we keep that as 1. If we haven't processed this node yet, we'll keep -1 to indicate that this is not processed yet. So let's look at the code and for partitioning this, and later we'll look at dynamic programming in order to get the actual path. He actually asked is the path the coloring of this nodes. We'll get into that. So first, let's look at code. So this is number of nodes, n is number of nodes, and m is number of edges. The color count is n1, this n1, right? N1, n2, n3. I store it in a array called color component here, and this g represents the graph edges. So so I declared the maximum n. Since I'm declaring this variables as globally, I'm declaring a constant variable capital N, which stores the maximum. So I read this variables here in this function, and this partition of stores which partition, either 0th partition or first partition, this specific node ID belongs to. This specific node belongs to. So the count of 0, when processing, we'll use this count of 0 for 0th partition count, and count of 1 for the first partition, 1th partition count for each of the component. When you're processing, we'll use this. And these partitions, what it stores, these partitions is a we have two such things, for one for 0th partition, one for first partition, and each of this is a 2D vector which stores each row is represents one segment, that is one component, one isolated component. We'll store such components nodes in this. So this partition size is actually this is the size of each of these components, okay, each of these isolated components nodes. So let's see the solve. Here the process starts. We'll set all these values to initial values. This is we are clearing all these partitions because if there are some other test cases, I have written this. And will this for n is actually taking the node id value from 0 to n. So if this is not partitioned yet, we are storing -1, right? So if this is not partitioned yet, we are trying to partition this node. So this is nothing but isolated component, first isolated component. So we'll put 0 while we are processing, right? While processing, we are partitioning this into 0th and first partition. So the count 0 will store how many nodes in the 0th partition, and count 1 will store how many nodes in the first partition. So yeah, and this partition of id. So initially, while we are processing, we call this is belongs to a 0th partition directly without sorry, this is not penny. Yeah, we are partitioning this as, we are labeling this as 0th partition, and when we go to the next its tails, we label them as first partition like this, and again we'll toggle that partition, and again we'll toggle that child node partition. Okay, this one here, one here. This is what we are doing here. So we'll set initial this isolated component node as first node as 0th partition, and this partitions of 0 will store 0th partition nodes of this specific component. Now we are processing this specific component, right? Here it stores 1 and 3 stored in here, okay, in 0th. And sorry, wait, my PC got yeah, and this two, all these tools is stored in the other, in this array, okay, in this vector. So what we do is we have written this partition function which partitions this. So if you're not able to partition, in the sense we print no, it's no such coloring exists. So when you reach this partition, if you have set this node id partition here, right? So if this belongs to a 0th partition, we'll increment the 0th count, and if this belongs to a first partition, we'll increment this count, first count. And this we need to push to the we are actually appending all these segments, all these component nodes one by one. So the last will contain the current component vector. So in that we are actually pushing this node id, okay, and then we'll iterate over child ids, and if this is not processed yet, then we'll toggle this. Here we are seeing this, we are toggling from 0 to 1, 1 to 0, 1, 0 to 1. Similarly, now we'll put that, and we'll partition the child nodes. If the child node partition is not able to process, we'll return false. If the if there is a cycle like this, let's say let me take this, let me change the color of pencil. Let's say there is some sort of cycle edge here which forms a cycle. So since you are having one here, you're using this as a parent current node id, and the child node is this. So if you already processed this before, whatever the labels, that whatever the partition that you are having, it should not belong to the same partition, it should be belongs to a different partition, or you can say that as yeah, that should be belong to different partition. That's what we are checking here. If the node id of partition belongs to the same of child id partition, we'll return false. If not, we return true. This is how we are partitioning and actually storing the nodes, okay. Now we have done this partition, and here we are storing the 0 at the, so these components, these isolated components, 0 at the partition nodes count and 1 the partition node counts. So this is all about partitioning. So now we need to dive into how tackling multiple components. It's not single component, right? So it have multiple components. We need to process all these components and see whether we are able to fill these colors. Okay, so let's say in first graph you have in first this component you have let's say x1 nodes. Here x1 for part belongs to a first partition and x0 belongs to 0th partition, and you're having y here 0th partition, and y1 belong to first this 1th partition. This is a different component and this is different component. They are isolated components. Similarly, you can have multiple isolated components here. So what we do is, if you are able to reach this state, we are considering each this as a TP states. If you are at this component, and if you have these many colors, these many two colors, now we are only concentrating at coloring with twos, because we are trying to select either filling these 0th partition with twos, or either selecting the 1th partition with twos, because one of this partition we fully fill with 2, the other partition we fill with the 1 and 3. So we are concentrating now on filling the one of the partition with twos, all twos. So the TP state will use the TP, and the TP state the TP state is like this. So the first dimension is number of component. What is the number of this component? Number of components. And n2 means which is a color of second color, like count of second color. So what it means is, if you're at ith position and dp of I comma j, we set this to true. Like here we are setting with the different status colors. If this is -1, then what does it mean is you can't reach this state. You can't reach this state. So what does it mean is there exists no such component, number of components with these many two colored count. We can't paint these many components with this two color count. That's what this state defines. So the 0 states, if we store a 0 there, it means this is the case. This state is reached by taking 0th partition and filling with those with two color from a I-1th component. Okay. Or similarly, if you store 1, we took this 1th partition and filled with two color. Okay, we filled with 0 means the previous component we filled the 0th partition with two color. If you store 1, we fill it with 1th partition with two color. Okay. Let's see how this is implemented. So this gives you the total number of components you have. Okay, and we iterate over all the components count, and we iterate over all the possible color counts. Okay, it can be will start from 0 to n, even though we this is a sub problem that we are solving first. This is a bottom up approach of this dynamic programming. So if this state, you can't reach this state, then you can't propagate this dp values to future states. Okay, future components, next components. So if you're, that's why we fill it with 0 0 with 0. This is the base case. That is means you have 0 components and you have 0 colors. You can fill with this is possible, either you can fill 0 or 1 here, that's up to you. And if this is not -1, means that you are able to fill C components with n-2, sorry, this n2 colored nodes, n2 color count. Okay, so if you are able to do this state, then you can go to the next state, that is C+1. That is C+1 number of components with these many and we have stored how many 0 at the partition count, right? Here this value gives you the number of 0 at the partitioned nodes that you have in the current component. So you use this to get the next state, and since you're coming from the 0th state, you'll fill 0 there. If you're coming from 1th state, that is 1th partition, then you're filling with the 1. I think the idea is clear. So this is how we fill the DP. So I'll open this folding so that you can see the code. Okay, so now you are reaching you have calculated all these DP states. Now what we want is, you have all the components now, all these isolated components, and you have these many color. You remember or not, this is a color count that we have read initially, where we store the color counts. Here we store the color, we read the color counts, and we store that. So color count of at indices 1 is actually the count of two labeled color. Okay, I think the idea is clear. So this will give you how many such color, this will give you how many two labeled color exist. So if you are not able to fill these many components, all the components with this given two color, so there is no way of coloring all other nodes, so there is no way of calculating the label. So now the other task is, you need to calculate the label. So you need to assign colors to each one. So this can be done easily because we can use a backtracking here. So since we stored so before component, from which partition partition we have come from, we have stored it in this DP, right? So we can use that in order to get the label, that is in order to get the colors of all the nodes. So initially this color count is given, right? So now so we'll take the component count, so last component, and here we'll get all the nodes that are belong to this specific partition. So we have stored, so this DB will show which state, that is which before components partition we have come from. So this gives you where I come from. So we need to get those nodes. We stored the nodes of 0 at the partition of specific component in this partitions vector, right? So since the component ID, so since it's stored in 0 indexed, the component ID you can get that by C-1. So in this way you'll get all the nodes that need to be processed. So you'll fill that with a color 2, and you reduce after processing all this, you have used this many number of the size of this vector number of colors, right? You fill those nodes with 2, so you reduce that count here, and then you process similarly by reducing going to the before component, and we have already have the state in the DB. You use that state and fill that colors. So and now what you are left with is, you have filled all the nodes with color 2. Okay, now you need to choose the color 1 and 3. You can choose in a linear fashion, and you can fill whatever you want the color in 1 and 3, because they are belonging to the same partition. So you can fill the color of 1 or 0, it's up to you. 1 or 3, it's up to you. So you fill all the colors till 1 got consumed, and then you'll use the color 3. So and then you'll iterate for all the nodes, and you print all the color labels. So I think this is a pretty long video, and this is how you print the color nodes. I think you understand the solution. This may be a bit confusing. You watch this video again 1 time and 2 times, so you'll get an idea of how this get. And moreover, one thing I need to point out is, I haven't solved this question. I have solved this question. I read the editorial. The tutorial is pretty neat, and this question is awesome, because of which I would like to explain you. So I will show you the editorial that I have read. So it's a Codeforce editorial, you can read there. So it's loading. Okay, you can read that Codeforce blog editorial. This is very interesting. It combines a few concepts. So my internet is pretty slow. I will put the link in the description below so that you can read. So here is the explanation. So my internet is pretty low, so I'm not able to. So I will put the link in the description below so that you can watch that. This is very interesting. I learned a lot from this, so I'd like to make a video on it so that you can learn something new. And like always, don't forget to like, share this video and subscribe, because that gives you boost that gives you boost to make more videos like this. I feel and I hope you learned something from this video. And thanks for watching, and stay tuned, and bye bye.